So I would, good morning. I would suggest we start our session then looking at the time. So first of all, Uli sends his apologies. He has unfortunately a conflicting meeting right now, and so he asked me to fill in and moderate the first session. So there would be two parts. The session is divided into two parts. The first part of this breakout session is this morning, and then in the afternoon, the second part. The idea is to discuss about digital agriculture for sustainable production. There will be 3 presentations to set the scene. So we are doing this because we're coming from the research center Jülich. We are interested in developing, applying software, hardware solutions to understand plant environment interaction and transfer this into application. And as such, using of digital agriculture is one of the key core questions for us. And we also managed to get key speakers in this involved working in this area. For the session now, we will have roughly 8 minutes for every speaker to introduce their topic. So the first speaker will be Michelle Watt from the University of Melbourne, talking about below ground challenges. The second speaker will be David Han from Phenotrade, talking about the difference between digital and in the end making meaning from digital, so smart agriculture. And finally, Uwe Rasche from the Research Center Jülich will talk about exploiting synergies across scales, talking about scales from single plants to entire fields, from ground-based to satellite-based measurements. And as such, may I ask you, Michelle, to start to give your presentation. I hope you can share the screen, and you are welcome to talk about your below ground world.
Okay, no problem. I just
or would you like me to share the presentation?
Yeah, I can actually do it. It's probably easier. I thought the organizers were going to share it, but I actually have it here, which is great. And I will share it right now. Okay, super.
Thanks a lot.
Everybody can see that. Yeah, sorry about this PDF stuff. Thank you very much for asking me to speak at this meeting. I am going to focus on what I see as the most important challenge for this century in agricultural technologies, and that is the quantification of carbon and water and nitrogen below ground. And I'm going to go through the talk really giving 3 reasons and opportunities about why this is such a critical challenge that I think the new digital technologies can address. So below ground, in the soil underneath our feet, this is filled with the roots of plants and their associated microbiomes, the microorganisms that are associated with the roots and obtaining carbon that's been fixed in photosynthesis above ground, goes below ground. And this very significant carbon pool, terrestrial carbon pool, is so far unmeasured. So we have this large part of terrestrial carbon going below ground, and it's been very, very difficult to quantify and measure. And I'm going to give 2 critical examples of where it's not included so far in both models and in estimating yield gaps. So as I highlighted, I mean, the really critical thing is that carbon is fixed in the leaves of all plants in photosynthesis, and a portion of it stays above ground in the leaves and the seeds and the flowers and the harvested products above ground, but a very large part of that carbon goes below ground into the roots and then out into the soil. The roots then in turn return water and nutrients up to the leaves to build biomass. And for over 100 years, we've had a problem quantifying this below ground, these below ground processes. A brief history of the story of crop improvement and climate change concepts. And essentially the history has been one of avoiding directly measuring the root carbon, water and fertilizer below ground because of the challenges associated with these measurements. And what I want to show in this timeline, I'm not going to go through it in detail, is that we have had last century a series of experiments and key sort of phenomenological concepts that have come together to basically arrive at a way that plants are modeled, measured and modeled. And most of the global models for agriculture and also for climate estimates have a very round number of 25% of the plant biomass going below ground into roots. And the actual measurements for this number originated from weighing of the root systems back in the 1960s. And really largely based on the Farquhar-von-Kammerer model, some critical produced by Sinclair and others related to radiation, water, and photosynthesis, we have been estimating below ground based on above ground. We have not been directly measuring it. Sorry. So what I'm going to show just briefly in this slide here is a selection of measurements that were actually done of below ground biomass from both field and pot experiments on the crop wheat. Wheat is one of the largest and most important crop for food security, and it's the most widely grown geographically on the globe. And these actual measurements show a very wide range of carbon below ground biomass and associated compounds going below ground from 3% all the way to 69%. A mean of these actual measurements, more recent measurements, is 41%. And really the message here is that we can do a much better job of estimating and quantifying below ground carbon compared to this number we're using from the 1960s with today's new technologies and even more new technologies that can be developed. The second point that I'm going to make about this below ground biomass and carbon is that yield gap estimates, these are used to estimate where yield gains can be made globally, do not include root and microbiome biomass. So basically in this image here, this is a standard grass crop. Typically what is done is that the components of the crop are divided into what's called a yield identity, which is the amount of resource used, times the biomass that's produced with that resource, times the harvest index, the amount of biomass that goes into the grain. And this identity and the yield gaps are used to see where we can make new innovations, and they do not currently include below ground carbon. Sorry. Okay, and here in this figure is just an illustrative graph of what is a yield gap. So yield gap analyses are central to global investments. And it really is important that we include below ground processes in these analyses. And a yield gap is shown by plotting the resource that's critical to the analysis. soil, water, nutrients, or radiation, for example, or even land, against the yield that's achieved for that amount of resource. There's a boundary line for the potential that can be achieved depending on the crop and the genotype. And basically, this boundary line can be moved up, either with more yield because of the roots functioning better resource efficiency because of the roots capturing more water, or increased carbon sequestration. Now, finally, I'm going to say that new technologies can be used to better estimate this below ground biomass and carbon across the globe. Today, in a recent review, we showed all of the technologies that have been tested so far historically to estimate below ground biomass and carbon and measure it directly. These extend all the way along the electromagnetic radiation spectrum. Some of them can only work in the lab, could be transferred to the field, and some of them can work in the field, but very poorly for non-invasive measurements. They're very low resolution. For field estimations, we rely on either digging or coring the roots, imaging them in a window below ground, or indirect measurements by measuring canopy. And with initiatives that are going on with agricultural technologies, these are digital and robotic technologies, advancements in sensors. I really believe that we're going to be able to advance below ground quantification this century. And this is probably going to be able to be achieved through a hybrid of very high resolution phenotyping technologies used in controlled environments and field technologies. The advantage is that sensors used in the controlled environment and lab experiments often are similar to the sensors that are actually used in the field. And I think Uwe will highlight this. And Uli Schur, along with colleagues in the University of Bonn in the DFG Excellence Cluster, really are focusing on this challenge of getting digital technologies used in this century. And with that, I just want to thank my colleagues, past at CSIRO, and most recently at the Jülich Forschungszentrum, and now my colleagues at the University of Melbourne. Thanks, Roland.
Thanks, Michelle, for the fascinating below ground world. I would suggest we move on now to David Hahn from Phenotrade to introduce digital and smart agriculture. Can you present? So may I also ask the participants, if you have any questions, put those questions into the chat. We will address them at the end. The goal is to have now half an hour presentation setting the scene, and in the end have some time to discuss, and your questions should also be addressed. But David, the stage is yours.
Okay, thank you, Roland. Thank you, Uli, to give me the chance to present my opinion for digital agriculture and smart agriculture. My talk will be how far is it between digital and smart agriculture. So as we all know, we have a global population booming. We will increase our population into 10 billion in 30 years. So we need more food, but we only have limited farmland. So we need to have higher yield. And also we have people become more wealthy, middle class increasing. So people need to eat more meat, more protein. And also the population was aging and birth rate decreasing. You can see here that in China, the agriculture, the farmers' age was rather high. So it's very serious aging trends, and also the education level was rather low. So which means we need more robots in future 20 or 30 years. And we meet very serious climate changing. The past 5 years have the top five high temperature since 1880. So we need to have more stress tolerance, stress tolerated plants. And we need environmental sustainability. So we need to import, we hope to import less chemicals to our farmlands. And this year we all met a pandemic. So many farmers, many breeders hope to remote monitor their crops and do the management automatically. So the agriculture faces challenges, and what we need is to make the agriculture more digitalization, more smart. For digitalization in past 30, 40 years, we can collect a lot of climate data, soil data, and in past 15 years, the technology to collecting plant data developed very quickly, which was called plant phenotyping or plant phenomics. So we can collect the plant phenotyping data now, and other omics data like genomics data was very cheap, and we can collect a huge amount of sociological data. So, and all this data was coming from different sensors, different sources with different format. So we hope to use this data to make the best model. So we have the modeling process. We need the artificial intelligence to be involved, but modeling is not the end. Our purpose is to make a smart decision. This is what we call smart agriculture. But after make the smart decision, we hope to have smart breeding, smart sowing, then go to fertilization, smart spraying, irrigation, weeding, and harvest. But that's not the end. Then we go to the downstream industry trend. But this is not the last, because agriculture is part of the society, it's part of the market, part of our world. So we hope to have the very smart decision for policy making, price making, economy, insurance, and also financial features. So, and all this data, all this generated data will go back to the database, and then to improve the models and improve our decisions. So in all this process, the key is the decision-making process. In order to make the decision-making process, in order to coming from digital agriculture to smart agriculture, we need to collect huge amount of plant phenotyping information, especially in field. So we can say that obtain plant phenotyping information, especially in field, is one of the key bottleneck of the smart agriculture. So here we give 3 examples which was widely used all over the world. The first one is data services. We all know that there are many companies who offer field climate data services. They collect data from weather stations, and they handling the data, they modeling, they provide services to farmers. But most of the climate stations in field, they lack the crop information, lack the images, or lack the NDVI or chlorophyll information. And some other companies, they collect the satellite information, they process in modeling, and also do similar service. But satellite images can cover large scale crops, but they only have very low resolution. They cannot arrive the resolution we needed. Another example is for UAV protection. There are so many drones used widely in the world, especially in China. In past, the big farmers, they purchased drones. Nowadays, they buy services. But most of the drones, they have cameras, but they cannot handle the images instantaneously. And handling images instantaneously, getting the phenotype information and making the smart decision is very important for the precise or smart plant protection. And the third example is agricultural machinery. This is a very major and huge amount market. They have very high technology now, and a lot of machines have GPS navigation systems. What my question is, can we add more sensors, imaging sensors or spectral sensors into these machines to collect crop phenotyping information? And can we do the instantaneous imaging processing and decision making in process in future? If we can do this, may be very useful for future agriculture. So from all these examples, we can see that plant phenotyping is very important, is one of the key process or key bottleneck. While plant phenotyping need multidisciplinary collaboration, we need engineers, we need scientists, plant science, or breeding, or genetics, we need mathematics, we need computer sciences, different disciplinaries to be involved. We need more international cooperations. There are so many plant phenotyping networks in the world. They do very well. And we also need more connections between academia and the industry. As I know that there are many research organizations invest a lot of money to research or develop the technologies which was already existed in industry. I think this is waste of money. And also, we need more open discussions and collaborations between different stakeholders and actors. So different stakeholders and actors, they have their roles, their purpose, their benefits. Sometimes they are not very open to share information or very open for discussions. We hope in future we can have more open discussions. And also, the last point is the development of AI and the instantaneous computing ability will accelerate this process, because only if we can make the instantaneous decision in field, in drones or in the machines in field, we can go to really smart agriculture. Okay, this is my presentation. Thank you.
Thanks a lot, David. Thanks for the very nice presentation about digital agriculture. So we would move on now to Uwe and to make a journey how to assess plants across scales. So Uwe, the stage is yours. Okay.
Yep. Thank you, Roland. And David, can you stop sharing your screen and then I can put up my slides, please?
Yes, I'm trying. Sorry.
No worries.
I don't know what happened.
Yeah, so thanks, Roland, and thanks, Uli, for inviting me here. I'm also working at the Forschungszentrum Jülich, and I also are affiliated with the University of Bonn at the agricultural faculty there. And for today, for the next 8 minutes, as Roland already said, I would like to talk about scales in measuring plant functions. And I would like to give you a journey from really the plots or the single plants up to the satellites. And by doing so, I would like to pick up some of the thoughts which were already prepared by David's talk. And for the start, just some images which I stole from web pages where different visions of digital agriculture or future agriculture are shown. And this all has to do with satellites, with drones, with smart machines on the grounds, and a lot of farmers which are being made available online to the farmer at the end. And if I try to actually sort this a little bit and to organize this a little bit, if I think about what elements are actually currently undergoing this technical revolution, I could come down to say, on the one hand, we are working a lot, or we have worked a lot on the sensors itself. We have developed in the past years novel sensors, like here in this case, an active fluorescence sensor, which can look into plants online while being on the field and to derive information about the structure and the function of the plant, which is unprecedented. However, speaking about novel sensors, I made my life easier because I'm mainly focusing on the above ground part, which is easier to be accessible. And I totally agree with what Michelle said. The below ground part is the challenging part, actually, to measure and to sense with our technology. Second aspect where we experience a technical revolution, or have experienced a technical revolution, is in positioning platforms. We have drones, unmanned aircrafts, which can fly easily and are cheap to be employed in agricultural production pretty straightforwardly. And third one, the robots which have been mentioned. There was a technical revolution of commercial robots which are now already available for the market, but also experimental platforms. And this is a picture of our experimental platform, which we further develop in the Excellence Cluster PhenoRob, where we test new measurement modes, where we test new navigation modes and sensor integration. But also on the robotic side, there's quite a lot of technical development having been happened in the past years. And last but not least, fourth pillar, all these elements nowadays can be linked based on the revolution which we have with machine learning and deep learning algorithms, which come mainly from autonomous driving or industrial processes, but where the processes, the software, the knowledge is now also transferred to agriculture and already shows up in the high-tech platforms of novel agricultural machinery. So these four elements, from my perspective, are the elements where we have and where we are experiencing quite some technical digital revolution. And now coming to the second part, to the scale, how do we actually link this across the scales? And there I would like to start on the really large scale, namely from satellites. And as you may know, in Europe, the European Space Agency is currently implementing a new generation of satellites, which is called the Sentinels, the Sentinel satellites, Sentinel-1 to 6, being on the way and more to be followed. And this is a new generation of satellites, which give us a really novel and really high definition view on our Earth's surface from all the different components, from the soil to the plants, to the oceans, the waters, and to the atmosphere. But if we look on the whole family of what is currently in the pipeline of ESA, this is an overview of the satellites which ESA is currently implementing. There is this Copernicus branch with the Sentinel family as operational satellites. There are meteorological satellites, and there's another branch of scientifically driven satellites which explore new technologies, new measurement modes for the future. And if I, for example, look at the newest member of this family, the FLEX satellite, this is a satellite which is currently being implemented to be launched 2023-24. And this satellite is specifically geared towards measuring photosynthetic activity of our vegetation to provide physiological indicator for vegetation health status or stress. And if you can see, one target region is really down to agriculture. However, what is also meant is that this satellite will only achieve a resolution of 300 by 300 meters pixel resolution in the revisiting time of a few weeks. So at the end, even though this satellite aims to measure photosynthesis as the indicator, an online indicator for threats on vegetation, and to also provide input for our sustainable agricultural production. And this figure actually is taken from the satellite mission, so not from a bioeconomy presentation, but this is really actually taken from the ESA documents. Nevertheless, the targets are the same, photosynthesis as the central indicator to be measured from space for plant production. We are still facing the problem of the resolution of such a satellite mission. And for this, I would like slowly come down and think about how do we actually come down to the scale which are important for farmers, for the end users. One part is to move down using aircrafts. One picture of our research where we have a demonstrator of the satellite mission being implemented in an aircraft, measuring according to the same measurement principle as the future satellite mission. And by this, we can already get down to the resolution of a few meters, resolving photosynthetic efficiency, really for actual photosynthesis on the scale of single fields and below. The Forschungszentrum Jülich with a open pit mining in this area, and this diverse agricultural system where every field, depending on the farmer's practice and the seasonal cycle, have different photosynthetic efficiency at the time of the overpass. And if we do some further image processing with the aircraft sensor, we can also move down inside single fields. This is an image of the agricultural research campus Klein-Altendorf of Bonn University, where you can actually see the experimental plots of the science campus. And by some image processing, we can move down barely to the size of experimental plots, which have a resolution of a few meters. But this is then most likely the limitation which we can achieve with aircraft sensors. And this is then, from my perspective, where, coming back to the beginning of our talk, where then the next platforms, UAVs and ground-based systems will come in to close this gap and really to scale down to the elements which we want to detect, namely early detection of stresses, of pests, and so on. So with this, with my last slide, from my perspective, there's a lot of technology development happening in all the different scales. However, the challenge for our future, I think, is really to now smartly link those different scales, which do not exclude each other. However, the smart modular linking of these different elements from satellite data, which are free, globally accessible, but still have the limited resolution, with aircraft data, which are an expensive product, but most likely still can provide relevant information for dedicated use on the intermittent scale. To use the capabilities of drones and unmanned aircraft as cheap and versatile platforms down to the point measurements from the tractor, or in the easiest way from the handheld smartphone application. And to link these elements, I think if we are doing this clever, this could be really the game changer in our digital agriculture for the future. With this, I think I'm at the end of my time. Of course, this is all a lot of international collaboration, and already David mentioned the networks on phenotyping, but there's also international networks to bring the remote sensing, proximity sensing capacities together on the national but also international level. And with this, I would like to thank you for your attention, and I'm looking forward to a discussion, and I hope that I have sparked some ideas with this. Thanks, Roland, back to you.
Thanks, Uwe. Thanks a lot. Thanks to the speakers for keeping the time. Now we have about half an hour for an open discussion. And so, Michelle, David, may I ask you also to turn on your video and basically start the discussion? So what we started, we prepared a set of few guiding questions, which you should be able now. So I would like to share the questions basically with all the participants so that you can see what questions we would try to address, and encourage all the participants to put also your questions into the chat. So I'm pretty sure there will be time also to address questions from the audience. But as such, we've seen there is lots of challenges below ground, using data in a useful way, addressing different scales, and as such, the first question would be, which is actually already on the screen, to all three speakers, complementary topics from your perspectives. What would be the game-changing technologies that will guide agriculture in the next 20 years? Should we start with Michelle? Would you like to start and basically address the game-changing technologies in the next 20 years?
Yeah, so as you saw from my talk, I really feel that there is a very big gap in not being able to quantify biomass below ground. This has implications for carbon sequestration measurements, political decisions to offset carbon with knowledge of carbon below ground. It has implications for understanding nitrogen capture by root systems below ground, and ameliorating that way. And also, as I mentioned, when we are modeling and looking for gains in carbon use efficiency or resource use efficiency by plants, we don't have approximately 50% of the plant estimated in those values. And yeah, I think we're really operating in the dark by always saying that above ground measurements tell us what's below ground.
Mm-hmm. Okay. Thank you. Maybe Uwe, right now when addressing these technologies, but also game-changing technologies, but this question above, below ground, what's your opinion?
Yeah, thanks, Roland. I totally agree with Michelle that I'm confident that your soil scientists will manage to look below ground and to see the roots and the whole biome below ground in the next years. This is definitely one technology. A second one where I'm pretty confident that this will be a key player is coming from data sciences. So when I currently observe what machine learning, artificial intelligence are developing on algorithms which are robust and also fast, enabling online data analysis, I'm pretty astonished. So years ago, we were still, could keep up with all neural networks with our physical models, but this machine learning approaches, I think, will surprise us not only in the next years. The problem is still that these data will need a lot of training to be universally applicable on the different fields in the diversity of our agricultural production systems. If you already think about how much effort goes into detect passengers from autonomous driving, how complicated it will be to detect diseases, the magnitude of diseases in the different agricultural production systems. So this is still a long way, but I would say this machine learning technologies will be a game changer in the future.
David, what would be for you the game-changing technology? May I ask you to briefly address that?
Yeah, I'm agree with Michelle and Uwe, especially in Uwe's talk he mentioned the SIF, solar-induced chlorophyll fluorescence. For me, I think those technologies which can detect the plant physiological states or forecasting the pathological states may play a very important role in the next 20 years. We all know that we have such kind of sensors. For example, we have half spectral cameras, multispectral cameras, chlorophyll fluorometers. But for half spectral, we know it's really powerful, but the data is really big, and we still lack a very major, very good algorithms which can be widely used. This is a very big limitation. The big data processing pipeline, especially with the help of machine learning, may help to figure it out in next 10 years or 20 years.
Okay, thanks a lot. Then moving on to the next questions, what would be the main obstacles that you see for those technologies to be effective? Uwe, should we start this time with you?
Sure. One obstacle could be, from my perspective, protectionism on all different levels. So if I was making the point in terms of, like, I think the different data streams, the different technologies have to be shared between the different players across scales, and I hope that actually we can come up to a really an open source, open user environment where data, software, and knowledge is shared. And I'm hoping that not only isolated high-tech solutions, which are closed solutions, will be there in the future, especially to transfer this to non-industrialized countries. I think this open sharing of technology software is really important from my side.
Would you, David?
Sorry,
Are we going clockwise? Or?
Would you, Michelle, address this question, the major obstacles?
Actually, I'm incredibly optimistic about the area of digital agriculture, basically because I think younger generations are very stimulated by these technologies. And I know what Uwe and David are talking about as well, but having, I guess, become involved a lot more in university teaching now for the first time, I really think it's an area that there are many aspects to it that are open source. Many, the robotics, the sensor, the computational area, and in some ways it's just the imagination. I see a lot of exciting opportunities in this area. It's more accessible than the genomic revolution, in my view.
Okay, thanks a lot. David, would you also?
In my mind, the main obstacle would be price, the cost. So even though we have the technology, and actually we have some nice technology already there, but can it be used widely? This is one of the biggest question we need to face. One of the biggest challenges is most of the technology are still too expensive to be widely used by the farmers. Yeah.
Thanks a lot. Before moving to the next questions, I would like to use the opportunity that we have representatives from the industry and academia and sneak in a question from the audience. So there is a question from Anna Soik about how big is the actual gap between industry and research-driven approaches in this area of digitalization of agriculture. So what's your opinion on this industry and academia-driven approaches to use technology, to use digitalization, to advance agriculture? Should we start this time? Michelle, would you like to start?
I think that's a hard question because I'm not in private industry, and it can be hard to know what is going on in private industry. So I really don't know what that gap is. It could potentially be quite large, actually. But on the other hand, based on the answer to my previous question, I don't believe all of what we're talking about here is expensive and big and flying around on a satellite. You know, we can be talking about possibly 3D printing and designing. Some aspects are very accessible, but I would imagine the gap between industry and research, it's probably large, but maybe Uwe and David can comment.
The gap, I think, it's really hard to see. The gap do existed. How to say that for industry, when we do commercialization and technology, the technology must be very well developed and can be used by everybody. So it may be not very, in some kind, it may be not very high tech, not very complex, but must be very reliable. In academia, the scientists are doing really nice research works. They can develop very high advanced technologies and publish papers, but how to transfer these technologies into commercialized products, it will cost a rather longer time. So in technology side, it's okay, we achieved, but in industry side, it's not ready. So with my experience, I thought the gap is quite big. It may cost many years to make the already existed technology to be commercialized. So if we can find some way to short this process, the other side, we are promoting the digitalization of agriculture.
Okay. Yep.
Uwe, yep.
Yeah, maybe some thoughts from my part. I agree. The big and difficult question. I think actually we do not have a big gap in the classical mode between industry and academia, because at the current which I'm experiencing is that in research projects, in development of new technologies, both partners from academia and from industry are actually working together in joint projects. And maybe this is also one of the big achievements of the fact that we have bioeconomy as a research and an innovation topic being recognized, because there really the researchers go out of their ivory tower and we work together and we directly sit together with the industrial partners within the same projects. So this is actually a big achievement, I would say, and there on your question, Anna, I think this was a great step forward to not have a big gap. The next thing is, however, how to bring then efficiently new technologies, innovation to the market. Where do we as a researcher stop, and where does industry really take over in the bringing then the things to the market? This is something where I think a lot of concepts were also developed in the framework of the bioeconomy, and this again is something where if I can pose a wish, I would wish that the pre-competitive level where industries are not in competition yet, that this level is being as big and as wide as possible, that we can really work together with all the actors before then the competition and the acknowledged interests of the single players in the market come in. So this would be my wish, to have this pre-competitive market as wide as possible.
Okay, thanks a lot. Then I would suggest we move on to the next questions, which partly addresses already issues that you already mentioned about this low-cost, high and low-cost technology for agriculture. So are there any differences? And I think this question already applies that most likely there are some between innovation aspects in high and low technology agriculture. How can they be addressed? David, would you like to start?
Okay, yes, they do have differences between the high-tech and low-tech agriculture. From my mind, most of the high-tech agriculture existed in the wealthy countries. The rich countries can invest a lot of money, and they can implement the high technologies into big machineries or robots. And they do not need to care about this the investment, because the farm is very big. You can use in the robots or machines to replace the laborers. But in low-tech agriculture, especially in the developing countries, they may do not have enough money for the investment, and they need affordable technologies. And also, for example, in China, we do not have so much big farms like in US. We only have we do have big farms in some provinces, but in most of the regions of China, the farm is really small. And many farms exist located in mountains, in valleys. So the big machine cannot work well in these small farms. So which means some high-tech machine cannot be used here. So how can we find a right way, a right technology to use here is also a problem. So we do have a big big differences between different technology or between different countries.
Thanks a lot. Michelle, would you continue? Would you like to continue?
Yeah, I would just really like to agree with David that I think one of the differentials of the technologies is farm size. That's really critical because in Australia we have the opposite situation. We have very big broadacre farms. And I think the key there, though, it's not that these farmers are wealthy, it's that their margins become very small, but need to be effective over a very large area. So they are using these technologies potentially in a, well, they're using different technologies, likely, maybe in a slightly different way to smallholder farmers, but I think I think the farming size and the operation will be a key driver of the type of technology, but there will be some underlying similarities, probably centered around the mobile phone.
Mm-hmm. Thank you, Uwe.
Yeah, totally agree to the farm size and the different management practices raised by you both. And the other thing, of course, is when we are talking about a technology-driven field, that it's totally illusionary to assume that this high-tech, expensive technology which we develop in the industrial countries can be transferred to developing or emerging countries. So what we are currently doing is we try to also actively make the big jump and work together with people where agriculture is in a change, where agriculture is still on a poor side. So we have, for example, projects in Nigeria, and I can tell you a lot of stories where we totally failed with our naive approach to take our high-tech sensors into the farming systems into Nigeria. There are hundreds of possibilities why this can be doomed. And how to overcome this, I don't have a master plan, besides that I think from the early on should try to work there internationally, invite the partners from the other countries to work with the industrial countries, and also vice versa, to make the early steps and to transfer our technology or our smart concepts into those countries. Even though it's sometimes hard, it leads to totally different thinking. But I think this early working internationally together, from my perspective, is at the moment the only way I can see to actually overcome this definitely problem.
Okay, thank you, Uwe. That would be your last sentence would be the transition to the next question. So we talked right now about game-changing technology, obstacles, industry interaction, low-tech, high-tech solutions. What do you think is the role or of infrastructure networking approaches to support this innovation? So how what do we need to do to develop networks for networking, to bring the solutions, to develop these solutions, and how should they be developed in the future? So what is your opinion on that? Who would like to start? Michelle, would you like to start?
Well, I think I'm going to hand over maybe to David. I think but just briefly, the international plant phenotyping networks that have been established by Uli Schur and European colleagues, and now globally, these really let a lot of people be involved very quickly in technologies. So I think that is really something to be fostered. But I'll pass to David, as someone in China, to talk much more on this, I think.
Yes, I agree with you. IPPN doing very well in this side. IPPN networking with most of the phenotyping players all over the world. Really nice job. And also, if we are talking about the infrastructures, I think Amphros is doing the best job in Europe, because you make almost all the big infrastructures together and offer opportunities, of accessible opportunities to a lot of scientists. While if I still want to talk something about China. If we talk about China, we found that networking is fine in recent years because more and more people began to talk about plant phenotyping, digital agriculture, smart agriculture. But we also have quite some infrastructures, but almost all these infrastructures are built for that organizations themselves. We do not have some kind of strategy or network-like emphasis to do that, which means there are a lot of scientists or big breeding companies. They have the request, they want to do experiment in big infrastructures, but they do not have the opportunity because they cannot build those infrastructures themselves. So how to make the organizations or scientists and also the industries more open, how to work more closely is a big question, is a big challenge in future years. If we want to do better, we need to work more closely. That's my opinion.
Mm-hmm. Yeah, and if I may follow up, and I go in the same line as the last question, which was just posed in the chat. I would also say there's a lot of things which can be learned and synergies which can be exploited if we move closer to the remote sensing and Earth observation community. This community has already managed to provide satellite data globally on platforms. I'm talking about Google Earth now, where you don't even realize the seemingly interplay and interlink of data sources from aircrafts, from different satellites, where you can zoom in the small scale out to the globe, and you don't even realize how the different data are actually linked. And with this community, which has a lot of experience of actually working internationally, making data available internationally, also in low-tech countries, I think there are already talks ongoing and started, and the example which was just posted in the chat is one good example of where this communication has been started. But I think this would be a field where we actually can exploit much more by linking these two communities who have just started to talk to each other.
Thanks, Uwe. And the question also in the chat is it addresses European Commission, so which also would lead to the next question about political constraints. So it would be very much interested about you. So when we have networks, we have technology. Do we need also support on the one hand from the policy sides? But do you see constraints, opportunities, how policy could support these developments on basically all those different levels, from networking to technology development to technology application? David, would you like to start?
Okay. Yes. In our country, the government release, they call it the State Council #1 document every January. In past almost 20 years, the State Council #1 document always have the topic of agriculture, which means the government really pay attention to the innovation-driven agriculture. But in other aspects, most of the content in that document is coming top-down. And there are some guidelines to the state-affiliated research organizations. So the government do not pay so much attention on the private companies, private enterprises. While I think the private players they have much more innovation power than the state-affiliated organizations in China. So we can say that the trends is very well, but the strategy maybe need to adjust a little bit. If we go back to digital agriculture or smart agriculture, I found in past almost 20 years in China, most of the players were coming from remote sensing or agriculture information field. Most of them, they have very nice background in remote sensing, in information technology, but they are not very well in plant science or agronomy itself. So we need to have more agronomy scientists to be involved in this way, because we are talking about agriculture, talking about plant is plant. So we want to resolve the questions generated by plant. So I think we do have the opportunities. We do have more and more opportunities for innovation in agriculture.
Thanks a lot. Uwe?
Yep, maybe quick answer as we're coming to the end. One constraint which I currently see is, especially in Europe, is the question who is allowed to look on a farmer's field, and are we allowed to use data from a private or privately used field publicly? This is something at the moment I see a constraint in this. How can we make data freely available? And there I would also advocate to have a free look of the whole society on our also managed agricultural systems.
I completely agree with Uwe. I think the power and the value here is the data, and the governments have a strong role in the accessibility of data and managing that accordingly. With genetic resources, we have a history now of not sharing, and that we have lessons to learn there. And I think the data value needs to be understood. Yeah.
Mm-hmm. Thanks a lot, Michelle. Looking at the time, we have already 10 o'clock. So I suppose there is one question in the chat, but I don't know if we have time to address this final question. If you agree, then I would go just for a very short comment. It's actually an interesting question about which technologies will be accessible and easily usable by small farmers. So there is within the next 20 years, there is this concern that on the one hand, there is this high-tech technologies which are available either by large agro-businesses, on the other hand by institutions developing novel solutions, but how could they benefit for the small farmers? Very short statements, please. Michelle, would you like to start?
Well, for me, I think already the use of soil sensors with a recording on a mobile phone, it's available, it can be deployed, and the ability to know when and how much to water would just add enormous value and resource saving to global agriculture.
Yeah, I can say something. For me, I think the as Michelle said, the cheap sensors and the analytical methods which can be linked to smartphone applications or technology which is already available, in combination with the access to the databases, to the potential machine learning approaches to help the farmer to detect, identify diseases, to detect or to see early signs of nutrient limitation already from normal RGB handheld camera systems. I think this would be one of the first technological steps which we can provide or can expect.
For me, I think it's some small drones have very high potential. For the smallest drones with a high resolution RGB camera, which can be used for phenotyping, it costs around 1,000 euros. So it's cheap enough to be used by farmers. What we lack is the data handling open source software. If we can find an open source software to be used by the farmers, okay, they can use the drones because the drones can fly, cover a very large scale of the farms.
Okay, looking at the time, so there are still some questions coming into the chat, but I would suggest the participants, I would forward the questions to the afternoon session. So happy to do that, forward it, and then I hope it will be addressed in the afternoon sessions. My impression is that we could continue the discussion for at least another half an hour, potentially much longer. It's an important topic, and we had experts who really could address most of those questions. There was lots of food for thoughts on technology, on digital agriculture, which is really important. So I would very much thank all the panelists for the presentation and for the discussions. So from my perspective, I really enjoyed it, and it was very enlightening, encouraging, and it makes a lot of how to look at new technologies. It's on the one hand, they are not only new technologies very exciting, but they also provide something very useful, and it's important to continue working on this in this field. So as such, thanks a lot. Thanks to all the participants, and I would like to also in the last sentence advertise for the afternoon session. So please join the afternoon sessions. The discussion will continue, and hope to see you in there. So Uli sure will moderate the next sessions. As such, thanks a lot, and hope to see you soon in the afternoon and at the coming up meetings and sessions. Thanks a lot. Bye-bye.